Okay, we're in 5.2 now. We're talking about large prime numbers. In section 5.1, I had brought up the subject of cryptography, which is the study or the science of encrypting and decrypting data, or encoding data is another way of thinking of that. A lot of algorithms that are used for the encryption of data involves prime numbers, specifically very, very large prime numbers. They're very secure algorithms because of that. Now, we can't really go into much detail because cryptography requires much more mathematical background than we can get to in this class. But we're just going to sort of scratch the surface. Now, section 5.2 is a little bit. It feels a little bit different than other sections we've covered, primarily because we're going to be talking about a few theorems or conjectures or kind of abstract things that are normally encountered at a much higher level of mathematics. If you take a full course in number theory, even an introductory course, it's usually not until you've had at least 2 semesters of calculus. Even though there's really no calculus that's used at an introductory level number theory course like this, the mathematical maturity that you obtain by the time you've gone through 2 semesters of calculus kind of give you the ability to handle those really abstract concepts and the very proof-based nature of everything. But anyways, 5.2 for us is really kind of an overview of some topics without digging too deep into them. So that's enough of my rambling. Let's go ahead and get into it. Like I said, the subject of 5.2 is large prime numbers. And an important theorem that allows us to even talk about really, really large prime numbers is the fact that there are infinitely many primes. Now, in 5.1, we talked about the sieve of Eratosthenes, which was a technique for finding all of the prime numbers between 1 and some other natural number. We did it for 1 to 100. And in fact, there were a lot of prime numbers that we encountered. There were 25, in fact. We didn't count them, but you can go back and count them. Within the first 100 natural numbers, you can find 25 prime numbers. That's a quarter of those numbers. But something that happens is if you continue that process well beyond the number 100 and keep searching for prime numbers, the further out you go in the natural numbers, the less frequently you encounter primes. And that may lead you to the assumption that eventually there comes to be an end of that list of prime numbers, and then everything beyond that is a composite. And that turns out to not be true. Even though you encounter prime numbers less and less frequently the further out you go in the natural numbers, we can actually prove that there's an infinite number of primes regardless of that. And there's a whole lot of different ways of proving this, but one of the first, this might actually be the first proof of this, comes from Euclid, an ancient Greek mathematician. He wrote the Elements, which is one of the most important, not only one of the most important works in mathematics, but it's considered to be one of the most important written works just in history, period. He proved the infinitude of the primes, meaning that there's an infinite number of them. And it uses a very common proof technique in mathematics called a proof by contradiction. Basically, the idea behind a proof by contradiction is you suppose that you're trying to prove some particular statement, P, let's call it. This is kind of using some of our notation from our Chapter 3 symbolic logic stuff. What you do is, if you're trying to prove the statement P, you assume its negation. You assume the negation of that statement, which symbolically we can write this way, not P. Remember, that's the opposite of what it is you're trying to prove. So what you're getting at here is that the assumption of the negation of the statement you're trying to prove should lead to some kind of logical contradiction. Which means that this could not have been true in the first place. But if the negation of a statement is false, then we know that that implies the original statement must have been true, which is what you were getting at the whole time. So that's the idea behind Euclid's proof of the infinitude of the primes, and we're going to walk through that proof now. So we would like to prove that there are infinitely many prime numbers. So what's the negation of that statement? Well, if there are not infinitely many prime numbers, then there must be finitely many. That's the negation. That's the thing that we want to show leads to a contradiction somehow. So we will assume that there are only finitely many prime numbers. And let's give them, names, P1, P2, and then there's a bunch here, and then Pn. Notice the list comes to an end. That's because we're assuming there's only finitely many. What we're going to do is construct a number out of these prime numbers in such a way that this number is not divisible by any of those primes. And that's actually going to lead to a contradiction. So here's the number we're constructing. We're going to call it m, and m is going to be a natural number that we get from multiplying all n of these prime numbers and then adding 1 to that result. P1 times P2 times blah, 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 all the stuff in between here, times Pn plus 1. Now, it seems likely this would be an extremely large number, but it's still a number, so it's valid to do something like this. Now, not only is it just a large number, but you can see that it's definitely larger than all of the prime numbers in this list. Okay? So that means m could not be one of the prime numbers in this list. Our assumption that this includes all of the prime numbers would imply that m is a composite number. Okay, that's got to be the case. Now, one thing we know about composite numbers from the fundamental theorem of arithmetic is that you can write any composite number in a unique way as a product of prime numbers, or it has a prime factorization. But if these are all the prime numbers, then I should be able to write m as a prime factorization of some collection of these primes here. Okay, so that's what this statement here is saying. M must be divisible by some prime number in this list. But the way that we defined m actually implies that that's not true. Because if I were to look at this product here, this product has every single prime number as a factor in there somewhere. So this product by itself is divisible by each of the primes. If m is divisible by one of those primes, then dividing m by that prime would cancel that prime from this product right here, but then it would leave a remainder of 1. And because there's a remainder of 1, that actually contradicts the assumption that m would have been divisible by that prime in the first place. That's the contradiction that leads us back to our original assumption, turning that into something that's false. So the original assumption, once again, was the fact that there's finitely many prime numbers. That contradiction implies that this assumption here must have been false, therefore there must be infinitely many primes. Now, if you've listened through that proof or read through it as I talked through it and are really, really confused or feel like it's very abstract, don't be alarmed by that. That's again, this is something that is normally covered in a number theory course, which again is at a very abstract level. But hopefully some elements of that kind of made sense. Okay, so the fact that there's infinitely many prime numbers means we can find prime numbers as large as we want them to be, because they never stop. And that's what gives us these very large prime numbers that are useful. Okay, so we're going to shift directions a little bit. And this is something what we're doing here is we're trying to look for different ways of kind of categorizing prime numbers, kind of understanding them on a deeper level. Something that's done a lot in number theory is called partitioning, specifically partitioning the natural numbers. You know the natural numbers to be the numbers 1, 2, 3, 4, 5, 6, and they go on infinitely. They go on forever. A partition of the natural numbers is a way of splitting those natural numbers into different categories based on some criteria. No natural number is allowed to appear in more than one category, and every natural number has to fall into one category or the other. So one partition that we could create is we could classify the natural numbers based on the remainder that we get when we divide them by 4. What that does is that gives us 4 different categories. Remember, when you divide a number a natural number by some other natural number, the remainder must always be smaller than the divisor. So if we're dividing by 4, there's only 4 possibilities for the remainder in those cases. If the number is divisible by 4, we'll get a remainder of 0. Otherwise, the remainder will be 1 or 2 or 3. So we can take the natural numbers, separate them into categories based on which remainder they end up with after dividing them by 4. Another way of writing the exact same characterization of these numbers is by splitting them up into these 4 sets. Set A, B, C, and D, where set A is the set of all natural numbers of the form 4k. K is some natural number. Again, this would imply that that number is divisible by 4, which means it would have a remainder of 0 if we divided it by 4. Here, numbers of the form 4k plus 1 would imply that you have a remainder of 1 after dividing by 4. Then we have a set for the numbers of the form 4k plus 2 and 4k plus 3. So this creates a partition of the natural numbers. If you want an idea of some of the numbers that are in this list, numbers that are divisible by 4, for example, are the number 4, 8, 12, 16, and so on. Right? So those are all divisible by 4. Numbers that are have a remainder of 1 after dividing them by 4, 5, 9, 13, 17, and so on. Numbers that leave a remainder of 2 would be 6, 10, 14, 18, and so on. Numbers that leave a remainder of 3 after dividing them by 4 would be 7, 11, 15, 19, and so on. And you can kind of see every natural number will end up being accounted for here. I could have put 1 in this list as well, 2 in this list, 3 in this list. You see all the natural numbers showing up: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. You'll get all of them. But none of them belong to more than one category. So this forms this thing that we call a partition. Okay? Now, the question that arises is which of these partitions contain which of these sets contain prime numbers and which ones don't? Well, I can say pretty quickly that set A and set C, aside from the number 2 showing up in set C, none of these will contain any prime numbers. Because look at those lists of numbers: 4, 8, 12, 16, 6, 10, 14, 18. They're all even numbers in either of these 2 sets. And remember, 2 is the only even number that's also prime. So aside from 2, neither of these sets will contain any primes because the remaining primes have to be odd. That means the only sets that contain odd prime numbers would be sets B and D. Okay? Now, why are we talking about this? Well, a long time ago, there's a very famous mathematician. His name was Pierre de Fermat. And he proved that if you pick any prime number that appears in set B, so notice 5 is a prime number in this set, 13 is one of them, 9 is not a prime number, even though it belongs to this set, 17 is prime, and so on. He proved that every single prime number that belongs to this set can be written as the sum of 2 squares, which is kind of an interesting little result. So here is an example where we want to try and do this. Both of these numbers, 29 and 73, if you were to try to figure out which category they belong to, they both belong to set B from the sets we defined previously. Dividing either of these by 4 will produce a remainder of 1. And those are the types of numbers that fit this theorem from Fermat. So what we want to do is try to find a way to express both of these as a sum of 2 squares. Now, what are squares again? Well, a square is a number that you get by squaring a natural number. So, for example, 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And then 25 is a perfect square. 36 is a perfect square. 49, 64, 81, and obviously the list goes on forever because I can square all of the natural numbers. But I'm going to stop this list here because these are enough to give me the results I'm looking for. And again, what are we looking for? I'm trying to find a pair of numbers in this list, perfect squares, that will add up to this number here. So as I kind of search through for 29, I see that 25 and 4 are both perfect squares. 4 is obviously 2 squared, and 25 is 5 squared. So there I found a pair of perfect squares that add up to the number 29. 73, what two numbers could I add up to make 73? We kind of start looking through your list. 81 obviously is too big to use, so I'm not going to use that. 64, I know that's equal to 8 squared. And notice if I did 64 plus 9, that would give me 73. 9 is 3 squared, and 64 is 8 squared. Okay. Now the theorem doesn't say that there's only one way to find a pair of squares that add up to the given number here. It just says that at least one such pair of perfect squares exists. The other set of numbers that contain primes, 4k plus 3, does not have this property. Some of the prime numbers in that set might be able to be written as a sum of squares, but not all of them. So it's something that's kind of a unique property of prime numbers that have this form to them. Okay? All right. We're moving on to still talking about prime numbers, but kind of a different concept, I guess. That's the word I'm looking for. So, again, the topic here is very large prime numbers. And there's been a number of attempts throughout history, none of which have been really successful, of finding a formula to generate prime numbers. So we know that there's techniques for, determining whether a number is prime or not, but to create a formula that just spits out prime numbers for anything that you plug into it, that has been a really evasive or elusive thing in mathematics. We haven't been able to find such a formula like that. One attempt to do this was made by a French monk named Marin Mersenne a long, long time ago. And he came up with these things that we now call Mersenne numbers. So a Mersenne number is a number of the form 2 to the power of n minus 1, and we use the notation capital M with a subscript of n. Mn represents this. N is always a natural number. So these numbers get very, very large very quickly if you keep plugging natural numbers into them, because exponential functions get very large very quickly. We call a number of this form, 2n minus 1, a Mersenne prime if this number happens to also be a prime number. Okay? So something kind of interesting happens with these Mersenne numbers. And again, we're not proving this here because our goal is not to prove these abstract results so much as it is to just kind of understand them on a basic level. If you you're plugging natural numbers in for n here. If that natural number is a composite, it turns out that this formula will always generate composites for you. If the number that you plug in here is a prime number, if I plug in a 3 or a 5 or a 7, those are prime numbers, then this formula will sometimes generate prime numbers and other times generate composite numbers. So as an example, we're going to find a few Mersenne primes. We're going to find Mn, where n is any one of these 5 values here. So in other words, I want to find M2, M3, M4, M5, and M6. Okay? So M2, what is that? The subscript tells me what I'm plugging in for n here. So that means I'm looking at 2 to the power of 2 minus 1. This is equal to 2 to the power of 3 minus 1. 2 to the power of 4 minus 1. And this will be 2 to the power of 5 minus 1. 2 to the power of 6 minus 1. That's what the formula tells me to do for these numbers. 2 squared is 4 minus 1. That would be 3. 2 cubed is 8 minus 1. That would be 7. 2 to the 4th power is 16, minus 1, that's 15. 2 to the 5th power is 32, minus 1, that would be 31. And then finally 2 to the 6th power is 64, minus 1, that's 63. Okay, now again, notice something here. One thing we're asked to do is determine which of these numbers are composite and which ones are prime. 3 is a prime number. 7 is a prime number. 15 is composite because it's equal to 3 times 5. 31 is a prime number that showed up in our sieve of Eratosthenes example. 63 is composite. It's equal to 9 times 7. Okay, so this is kind of confirming for these numbers the result that we stated up here. Notice the composite numbers that I plugged in for n are 4, that's a composite, and 6, that's a composite, and they produced composites in this case. When I plugged in prime numbers, 2, 3, and 5 are prime numbers, the results were prime. Now I said over here that if you plug in a prime number, the result could be prime or it could be composite. And so far we've only encountered primes in those cases. But that's not necessarily going to be the case every single time. So it turns out you don't have to look that hard to find an example where that doesn't happen. If you plug 11 in to that formula, if you find the Mersenne number M11, 11 is a prime number, but plugging it in gives me 2 to the 11th power minus 1, which is 2047. That is 23 times 89, which means it's not a prime number, it's a composite number. Okay, so that formula does not generate prime numbers every time you plug a prime number into it. So, decent attempt by Mersenne, but it didn't work. Fermat, that guy we talked about a little while ago, tried to come up with his own prime generating formula. And notice it looks kind of similar. 2 to the power of 2 to the power of n plus 1. These numbers get really huge really, really quickly because it's an exponential within another exponential. Fermat believed, or he conjectured, that this formula would create a prime number for every single natural number that you plug into this. In fact, even if you plug a 0 in for this, it produces a prime number. And it turns out to be true for the numbers 0, 1, 2, and 3, but pretty quickly we get to a case that's not true. N equals 4. This does not produce a prime number if you plug 4 in for that n right there. We can verify that just by plugging 4 in. 2 to the power of 2 to the power of 4. 2 to the power of 4 is 16. This is 2 to the 16th power plus 1 gives us this enormous number, 4,294,967,297. Now, it's difficult to tell whether this is prime or not. But again, using a number of different techniques or using computer software, which is much better at finding prime numbers than we are, or finding factors of numbers, this can be shown to be a composite number. So Fermat's little attempt here didn't work either. The tricky thing with Fermat's attempt is way back then, they didn't have all the tools that we have now to determine whether a number is prime or not. So he may have looked at this number, which is not hard to calculate. I mean, it takes a little bit of paper, I guess, but you can do this by hand without too much trouble. But determining whether this is prime or not can be really difficult without, kind of more modern tools, I guess. So that attempt failed as well. Now we look at a couple final examples here of formulas that people came up with in an attempt to generate primes. One of them is from Leonhard Euler, another very famous, very prolific mathematician, and his was a polynomial, n squared minus n plus 41. He used this to try and generate prime numbers. Now you can actually show without too much trouble that no polynomial can produce only prime numbers when we plug in only the natural numbers in for these n's here. And we're going to show you with this example why that happens. So it turns out that this actually does a very good job, a much better job than the previous two formulas at producing prime numbers. If you plug in the numbers 1, 2, 3, 4, all the way up to 40, it turns out, the first 40 natural numbers in for n here, this thing will produce a prime number for all of those values. But as soon as I plug 41 in, it generates a composite. And it's no coincidence that 41 is the constant term in this polynomial. This generalizes to other polynomials as well. When you plug the constant term in, something interesting happens. So watch this. If I plug a 41 in for my ends, this becomes 41 squared minus 41 plus 41, which I'm seeing right here. Now in this case, the minus 41 and the plus 41 cancel each other out, but I'm not going to do that quite yet. I'm going to instead look at this as still like a polynomial, and each one of these terms has a factor of 41. I can pull that factor of 41 out, simplify the inside, and now what I have is a product of two numbers, 41 times 41. So I didn't have to find 41 squared minus 41 plus 41 explicitly to show that it's just equal to 41 times 41, proving that it's a composite number. Another example of a polynomial that was come up with to try and generate prime numbers was later on. It was by a mathematician named E.B. Escott. And this was the formula he came up with: n squared minus 79n plus 1601. Again, this one, if you plug in the natural numbers 1 through 79, it turns out all of those generate prime numbers. Now, we could use the same thing that we did here in Euler's prime generating formula, or attempt at a prime generating formula, and plug in the constant term, which was 41, and show that, it leads to something like this. The constant term in this one's very large, 1601. It turns out that this fails to produce primes at a much smaller number than that. If you plug an 80 in, the result is going to be something that is not a prime number. So, and we're not gonna explicitly show that, but it can be verified without too much trouble. So again, this is kind of a different feeling section 5.2. Just because there wasn't a whole lot in the way of examples to do. It was kind of talking about some famous results regarding prime numbers and just sort of getting you a very, very surface level introduction into what number theorists do. So hopefully that was kind of interesting. We'll keep moving on with the topic of primes and divisibility throughout the rest of Chapter 5.